So take a look at this worksheet right here. Let's see. Cameron, you came up with a formula. Which one was it for?
It's 8.
It was for 8, and yours was it 1 over 3n plus 3? Okay, what did n have to start with?
0.
N would have had to start with 0. And then somebody else came up with a different formula. Who was it? Nathan, what was your formula? I think it was 1 over 3n, and what did n need to start with?
1.
N started with 1. Okay? All right. Let's see. How about this one right here? What could our formula be? N plus 1. If that's the case, what do we need to start n with? N would have to start at 0. Is there another one we could use? Okay, it could just be n, in which case n would start with 1. So of the two, which one's probably better? Probably this one right here, because most people would start counting with 1. And if we said this was the first term, and that was the second term, and that was the third term, and that was the fourth term, and so forth, it's probably better to start by counting it with 1. Let's see. How about this one right here? Anybody come up with one for that? Okay, n minus 2. And what would n have to start with?
4. Right.
Does that work? Start with 4? Okay, if I plug a 4 in, that would give me a 2. That's fine. Okay, will that give me, no, what would I plug in next? Okay, so I hear some disagreement here. Plug in a 2? Okay, so does anybody see a problem with, I mean, this wasn't too bad because we just plug in a 1, then a 2, then a 3, then a 4. And same thing down here. If we start with n equals 1, then the next thing we plug in is a 2, then a 3, then a 4, and it produces the right list. It produces the right sequence. Okay? Does anybody see a problem with this? How would somebody know that they're supposed to start counting at 4 and then go down to 2? And what's the one after that? Okay. Would anybody know that they're supposed to count by 2 going backwards to plug things into our formula? Okay. So do you see the issue here of coming up with a formula that everybody could understand just by looking at it? Okay. Somebody come up with something different, because that would work, but it wouldn't be very uniform or consistent or very universal. Okay, did somebody come up with something else? I mean, it's what's happening. What's that? What's happening as we go from term to term? What happens when we go from the first term to the second term? We go down by 2 every time, right? Go down by 2 every time. So I go down by 2 here, go down by 2 here, go down by 2 here. Every time I go from one term to the next, I go down by 2. Yes? Okay, so 2n, and then n would equal what? Then -1 and so forth. Okay, would that produce the right list? So if I plug in a 1, does that give me a 2? If I plug in a 0, does that give me a 0? If I plug in a -1, does that, okay? Does it work? It does. Is it as nice as these other two that we came up with, where you just start plugging in the number 1, then plug in the number 2, and then so forth? Okay? So again, the question is, how would somebody know they're supposed to start at 1 and go up, or start at 1 and go down? You'd have to write it out every single time, right? You'd have to write out what you start with, and then you'd have to show them, okay? We'd like something where you can just, everybody knows, if I've got a formula, what's the first number we should plug into the formula? 1 or 0, and which did we decide is usually better? Peyton, are you causing problems? Usually 1 is going to be better. Not always, but usually 1 is going to be better, okay? Noah. Okay, Noah's got a formula where we start with 0. What's your formula?
2 minus 2n.
2 minus 2n, and we're going to start with n equals 0. Okay? Well, let's see. If we start with 0, if you plug in a 0, you get a 2. Then if you plug in a 1, you get a 0. If you plug in a 2, you get a -2. So does this work? This is pretty darn good. Can anybody make one that would work if we started with n equals 1? 4 minus 2n. So let's try this. 4 minus 2n, and we're going to start with n equals 1. So if I start with n equals 1, I get 4 minus 2, that's a 2. So the first one works. If I plug in a 2, 4 minus 4, I get 0. Plug in a 3, 4 minus 6, I get -2. So does this one work? Okay, so I like both of these. Okay, if we're talking about, you know what? Okay, so listen carefully because this is going to play into what we're going to do in just a second in section 9.1. If I say this is the first term, and this is the second term, and this is the third term, and this is the fourth term, and this is the fifth term, is there anybody on the planet that would argue with us in saying this is the first one? Or this is the fourth one in the list, or this is the fifth one in the list? Nobody would argue with that, would they? So would everybody agree that there's a 1 associated with that term, a 2 associated with that term, a 3 associated with that term, and a 4 associated with that term? So, despite, unless Putin's going to make a decree, okay, it's probably better to start with a 1 and count up by 1 than it is to start with 0 and count up by 1. Not that you can't do both. You could do either one as long as you define that. But if somebody were to say something like this, you watching? If somebody were to say, hey, the formula for this one is 3n. Or the formula for this one is, anybody know what it is? Okay, let's just look at that one. If you started by plugging in a 1, does that make the right sequence? Plug in a 1, you get a 3. Plug in a 2, you get a 6. Plug in a 3, you get a 12. Plug in a 4, you get, ooh, wait a minute. Does that work? Doesn't work for that one, does it? Okay. 3, 6, 12, 24. Any ideas? Okay, it's doubling every time. Doubling every time. So they're not all these simple patterns like this. That's why I had you write down what the description of what the pattern is. This one is doubling every single time. So if I wrote this down, if I wrote 3 times 2 to the n minus 1, and I said that's my formula, and I said n starts with, what does n need to start with? What did we say was the best thing to start with? N equals 1. If I plug in a 1, I get 2 to the 0. That's a 1 times 3, so it produces a 3. If I plug in a 2, 2 minus 1 is 1. 2 to the first is 1. 2 times 3 is 6. Does that make sense? Okay. I'm just going to write this down, and you see if this works. This is all I'm going to write down. I'm going to write down 4, 3 to the n minus 1. If I don't tell you what to start with, what should you start with? Start with a 1. So I've got a first term, a second term, a third term, a fourth term, and a fifth term up there. Let's see if we can make this match up. This would be 4 times 3 to the 1 minus 1. Does that give you 4? Yep. This would be 4 times 3 to the 2 minus 1. That's going to give you 3 times 4, so that's a 12. Works so far. Just because it works for 2, does that mean it's going to work for all of them? Nope, let's plug in the one for the third term. 4 times 3 to the 3 minus 1. 3 to the second, that's 3 squared. Multiply it by 4, we get 36, so we're in pretty good shape. Let's check the last one. Okay, if it works for the fifth one, we're probably in business. This would be 4 times 3 to the 5 minus 1. Anybody know what 3 to the 4th is off the top of their head? 81, and 81 times 3 is? What is it? Oh, times 4. Times 4. So 324, right? Okay, so does this work? It does. Okay? So if you go through and you look at all of those sequences, it would be good if you could come up with a formula that works when you plug in a 1 first, then a 2, then a 3, and so forth. So we can produce the first term, the second term, the third term, the fourth term, the fifth term, and so forth. Okay? Because everybody, regardless of where you grew up or what you were taught or anything like that, everybody would agree that this is the first term, then the second term, and then the third term. So there's a 1 associated with the first term, a 2 associated with the second term, and so forth. Okay, any questions? Okay, did anybody figure this one out? What if you take 2 plus 2? What do you get? 4. What if you take 4 plus 2? 6. What if you take 6 plus 4? 10. What if you take 6 plus 6 plus 10? Next one should be 16. Okay? So the pattern here is, can somebody describe it for us? Add the 2 previous terms to get the next term. Add the 2 previous terms to get the next term. Okay? Did anybody come up with this one? It's something kind of similar. What's that? Subtract the previous one. 2 minus 1 is 1. 1 minus 2 is negative 1. Negative 1 minus 1 is negative 2. Negative 2 minus minus 1. Next one would be negative 1. Okay? And it'll go through and it'll repeat a pattern. Okay? All right. Any questions? Okay, so we're going to talk about sequences and series, introduce the notation and the concepts and stuff like that. Okay, so a sequence is a blank of numbers usually produced by a formula. Anybody want to take a guess at what goes in that blank? Set, or it's just a list. Okay. The easiest way to describe what a sequence of number is it's just a list of numbers. We normally separate them by a comma so we can tell the difference between a 1, 2 and a 12 if it didn't have the comma in between there. Okay. The book describes a sequence this way. It says a sequence is a function, or in other words, a formula, whose domain is the set of positive integers. The set of positive integers. So, what's the first positive integer? 1. Okay? So this is that standard uniform approach that we were talking about, that we were trying to arrive at by looking at those 10 examples there. Okay? You can come up with lots of different formulas, but it would be best if you could put the formula in front of somebody, and they know, oh, I'm dealing with a sequence. I need to start by putting in a 1, then a 2, then a 3, then a 4, and so forth. Okay? So each individual entry in our sequence is called a term, and each term has a counter that we call an index. Okay? And the index is a subscript. It's the number that you plug into the formula. So if somebody says, hey, I've got a sub n, okay, that's what we call the nth term of the formula. Okay? So this is a general formula that's going to produce a sequence. And if I go through and I put the indices on here, the counters on each one of these, this would be the first term, the second term, the third term, and the fourth term. So again, because it's the first one, there's a 1 associated with it, there's a 2 associated with the second one, a 3 associated with the third one, and so forth. And that index tells you what you plug into the formula to produce the term. So if I plug a 1 in here, I put a 1 right there. Notice that that index goes in both places. It's the counter for the term you're on, and it's the number you plug into the formula to produce the term. So what's the first term? 2. What's the second term? 4. Plug in a 3, you get a 6. Plug in a 4, you get an 8, and so forth. Okay? So this is a general formula, or an nth term formula we call it sometimes, and this is what we call expanded form. Okay? So you've got problems on your assignment where they give you a formula, and literally all you have to do is you have to produce a couple of terms. Usually they ask for 4, so that's what I've asked for here. So if you take a look at this one is written just a little bit differently. This doesn't say b sub n, this says b of n. So again, it's emphasizing the idea that a sequence is a function where what you plug in are the positive integers. So what's the first thing we're going to plug in? We're going to plug in a 1. So b of 1 is, plug in a 1, I get a negative 1 on the top and I get a 1 on the bottom. So the first term is negative 1. If I want the second term, I'm going to do b of 2. So that's going to be negative 1 squared, so that's going to be a 1, and the denominator is going to be a 2. So this is going to be 1/2. For the third one, or in other words, b of 3 or b sub 3 if we were doing it with subscripts, this is going to be negative 1 to the third, so that's a negative 1, and the denominator is a 3, so negative 1/3. Okay, now taking a look at that pattern and knowing that you could write this one this way, what's the next one in the sequence? Positive or negative? Positive 1/4. Okay, this is a good thing to keep track of. This is the way you make something, what we call it is we call it alternate. Okay, that's the way you make a sequence alternate. Is you have a negative 1 raised to a power, because every time it's going to go from being to an odd power to an even power, and it's going to change sign. Okay, so the next one we're going to take a look at is this notation right here. Have we seen this before in this class? Okay, has anybody seen this? Okay, a couple of you. Okay, it's called a factorial. Okay, and here's how we work with a factorial. So n factorial, and we say it just that way. We say n factorial is a short way of writing a long multiplication problem. Okay, it's used in a lot of different areas. We're actually going to use it toward the end of this chapter. So it's something, well, actually, I think next week we're going to use it. So if I say 5 factorial, this is the multiplication problem that this represents. It represents 5 times 4 times 3 times 2 times 1. So if you multiply all those together, that's 120. If I do 4 factorial, that's 4 times 3 times 2 times 1. Oops. So that's 24. 3 factorial would be 3 times 2 times 1. That's going to be 6. 2 factorial is 2 times 1, so that's going to be 2. And 1 factorial is just a 1, so it's a 1. Okay, what is 0 factorial? Okay, it would be interesting if it were 0. It's actually not. Okay, 0 factorial is a 1. Okay, and there's a couple arguments that we can go through here. Okay, you'll notice that every single multiplication problem right here has a 1 on the end of it. There's always a 1, and then the number in front is the thing that leads the whole thing off. Okay, so there's got to be a 1 in there. Okay, so even though there's not a number, 0 represents no number, we would say that that's 1, and then we could go through a quick proof of this. Okay, and it's based on the fact that if I write n factorial, and this is something that you'll want to keep track of, if I say n factorial, that's the same as n times n minus 1 factorial. So let me show you what I mean by that. If I say 5 factorial, couldn't 5 factorial have been written as 5 times 4 factorial? Wouldn't that work? Okay? Now, if we use that fact and the fact that 1 factorial is 1, divide the equation up here by an n. So this is going to be n factorial over n minus 1 factorial over n. Okay, this is going to cancel, right? Now, what happens if n is equal to 1? So if this is a true equation, this has got to be a true equation, right? What would happen if I plugged in a 1? So there's going to be a 1 here, so this would be 1 factorial over 1 equals 1 minus 1 is 0 factorial. Well, if the top is 1 and the bottom is 1, this side is 1, and what does it equal? Equals 0 factorial. Okay? Take a little time thinking about that. Okay, but that works perfectly well. Any questions? Okay, so if I want to say C sub n is 1 factorial, then C sub 1 is 1, C sub 2 is 2, C sub 3 is 6. I'm just going up this list right here, and C sub 4 is 24. There's our list of numbers. 1, 2, 6, 24. There's our sequence. Okay. Any questions? Okay, you can have some really weird ones, like on this one, if we plug in a 1, you're going to get 1 over e. What happens when you find the second term? What do you get? 2 over e squared. Next one, notice there's the index that we're going to plug in here. This is going to be 3 over e cubed, and then 4 over e to the fourth. Okay. Any questions? Okay, I'm going to show you how to do this one right here. It's no more difficult. In fact, it's probably easier than the last one. I do want to show you that you may not always want to simplify things just so you can spot the pattern. So if I write out the first 5 terms of this right here, if I plug in a 1, I get a 1 over a 3. There's the first one. If I plug in a 2, what do I get? 2 on top. Okay, so it's going to be 2 over 4. Okay, if I plug in a 3, I get 3 over 5. Okay, take a look at this pattern so far. Notice how the top is going up by 1 every single time. First term has a 1, second term has a 2, third term has a 3. And the bottom, the denominator is always 2 more than the numerator. I mean, you can see that in the formula. Top is n, top is 2 more than n. So we can just fill out the other 2 of these. This is 4 over 6, and this one's going to be 5 over 7. Now, compare that with what I'd get if I simplified this. My list would look like this: 1/3, 1/2, 3/5, 2/3, 5/7. So if you were looking at this versus looking at this, which one would be easier to spot the pattern on? The second one, this one right here, the one that's not simplified. Okay? If you simplify fractions, it makes it a little bit harder to see the pattern. Okay, are there any questions? Okay, what if I asked you what's the 101st term of this sequence right here? Could you find it? What would you do? Plug in 101, right? So you'd have 101 over 103. Okay, so the cool thing about an nth term formula is, unlike some other things where we were adding the first 2 together to get the third one, then add, the 2 previous ones to get the next one, you don't have to go up and find the 5th one, the 6th one, the 7th one, 90th one, 91st, 92nd, and all the way up to the 101st in order to find that. The cool thing about a formula like this is you can plug in the term you want. Plug in the index or plug in the positive integer that's required to make that term, and you've got your number. Okay, you've got the term. Okay, any questions? Okay, so we'll need to go from formulas, nth term formulas, to the sequence. We'll also need to be able to go backwards. Okay, so what we were talking about on that practice worksheet I gave you the other day. So you're going to need to be able to find an nth term formula for it. Okay, so let's take a look at this one right here, and let's call this a sub n, and let's come up with a formula. It's going to be a fraction. If this is the first term, the second term, the third term, the fourth term, and the 5th term, and sometimes that's helpful to write that down, okay, Or you could write something like this: a sub 1, a sub 2, a sub 3, a sub 4, a sub 5. We want an nth term formula there. Brandon? N over n plus 1 is the suggestion from Brandon. Okay? Is the top exactly the same as the index, the term we're on? Yep, so it's going to be n. And what's the relationship between the top and the bottom on every one of these? The bottom's one bigger. Okay? So we know the next one in this sequence should be 6 over 7, right? And that's going to be the sixth term. If you plugged in a 6, do you get 6 over 7? If you plugged in a 2, do you get 2 over 3? You do, so that's the right formula. Okay? So I'm going to write this one as b of n Isn't this the one we did? Yeah. 1 over 3n. And there we go. Okay? Now, this one here might be a little bit more challenging, so I'm going to do c of n for this one. See if you can come up with a formula for that. And when you've got it, raise your hand. Okay? Got 2 people? 2.5. Okay, go ahead and put your hands down. Who's got it? Okay. Noah, what'd you get?
I got n over n plus 1 times n plus 2.
Does that work? Okay. Stop and think about how you describe the relationship. I mean, most everybody could figure out what the relationship is here. The top counts up by 1. And this factor in the denominator is 1 bigger than the numerator. And this factor right here is 2 bigger than the numerator. So this one's n plus 1 and this one's n plus 2. Okay? If we plugged in a 5, I get 5 on the top, 6 and 7 on the bottom. So we're in business. That works perfectly well. Any questions? Okay. All right. So there's another type of formula that isn't as nice as an nth term formula or a general formula for a sequence. Okay. But it can be very useful. Okay. It's called a recursively defined sequence. Recursively defined sequence. And with a recursively defined sequence, they use some of the previous terms to figure out what the terms are that follow that one. Okay, so we've already looked at an example like that. Okay, and because you have to have a place to start with, and then a formula to get from one term to the next, or a couple terms to the next, you have to have this. You've got to have a first term. Okay, or maybe they've got to give you 2 or 3 first terms. Okay, the first one and the second one, third one, or something like that. And then they've got to give you a formula to get from the terms you have, or the terms you know, to the next term or the next terms. So this one right here, example 3, is a recursively defined sequence. A sub 1 is 3. That means the first term is 3. And then it says this. A sub n is 4 times a sub n minus 1. Okay, now here's the way to think of this. This is the next term. A sub n minus 1 is the one before it. So if you want the next term, you take the one before it, and what do you do with it? Okay, times it by 4. Okay, that little thing right there, notice that's in the subscript. Okay, so that's part of the index. That tells you what term you're going to use. So I like doing these this way. I like saying a sub 1 is 3, and then I'll put a circle around that. I've got that one figured out. The next one in the list would be a sub 2. It would be the second one. I'm trying to find the second term. So notice in this little formula that allows me to go from one term to the next term, I'm going to put a 2 right here. And remember, when I plug the index in here, I've got to plug it into the formula also. So that's going to be 4 times a sub 2 minus 1. Well, what's 2 minus 1? 1. So this is 4 times a sub 1. Well, what does this mean right here? What does a sub 1 mean? Well, it's the first term, right? And what's the first term? 3. So this means 4 times 3, so the answer is 12. So the next term is 12. So a sub 2 is 12. Then if I want the third term, I'm going to take 4 times a sub 3 minus 1. Or in other words, if I want the third term, what term am I going to use to make the third term? The second term, right? So that's going to be 4 times 12. So the answer is 48. Okay. To find the fourth term, I take 4 times the third term. So that's going to be 4 times 48. So that's going to be, what is that, 192? 192. Okay? What's the fifth term? 192 times 4. So every time you just times it by 4. So this is kind of an ugly way of just writing down a pattern where every time we multiply by 4. Take 3, multiply by 4, you get 12. Multiply by 4, you get 48. Multiply by 4, you get 192. Multiply by 4, you get 768 or something like that. Okay. Everybody good? Okay, take a look at this one right here. Okay, this isn't using the index idea. This is using the idea that a function or a sequence is a function. So when I say a of 1, what does that mean? First term. A of 2, second term. Okay. A sub k. Okay, I'm using a different index now. We used n's before. I'm going to use a k now. Okay. A sub k. We'd call this the kth term. This is the k minus 1 term. And this is the k minus 2 term. Okay, now I'm going to blow this up just a little bit, and I want you to think about what this means. If this is the kth term, and this is the k minus 1 term, and this is the k minus 2 terms, in terms of the order these terms are, can anybody describe these using next and last, or one before, or one before, you know, things like that? This is a recursively defined sequence. It gives you the first 2 terms, and then it says, hey, if you want to figure out any other terms, you've got to use this formula right here. So this is the, what did you say? This is the next one. Next term. What's this one right here? Okay, previous term, or I'm going to say this, 1 before it. And what's this one? 2 before it. Oops, learned to spell here. Okay, so if you want to make the next term, you take the 1 before it and the 1, 2 before it and add them together. Okay, does that make sense? Okay, so I'm going to write down the terms. The first one is 1, the second one is 1. In order to come up with the third one, notice what I've got here. I need the third one. I've already plugged in a 1, I've already plugged in a 2. I know the first and second terms, I need the third one. So if I plug in a 3, I get a of 2, and I get a of 1. Well, don't we know what these two are? 1 and 1, so what's the next one? 2. If I want the fourth one, that means I'm going to take the third one and add it to the second one. So the second and third one will make the fourth one. What's that? 3. Next one. 5. Next one. 8. Next one. 13. Does this look familiar to anyone? Who's seen this before? Raise your hand if you know you've seen this before. Okay. Anybody know what it's called? Yes. Okay, this is called the Fibonacci sequence. Okay? Pretty cool, the places this shows up in nature. It's pretty awesome. You'll find that if you go by a pineapple, you know pineapples have those little square patterns on them, or those little diamond-like patterns. They go around in spirals. If you count the spirals one way, it's always 13, and if you count the spirals the other way, it's always 8. Okay? Next time you're in a grocery store, check out a pineapple. And there are tons of other places where they show up like that. Okay? So, we're now going to change gears, and I'm going to introduce the next topic. We'll finish this up tomorrow. Okay? And then I want to show you one quick thing before we leave. Okay? So a sequence is simply a list of numbers. Okay? A series is a list of numbers that have been added together. Okay? Or in other words, we say they've been summed. Okay? And we can have sums that are partial, or we can have sums that are infinite. Say, whoops. Sums can be partial, adding just a finite number of terms. Or they can be infinite, which means they add up an infinite number of terms. And we use the Greek letter. It looks like this. Okay, I'm going to draw a crappy one. We use the Greek letter like this. Looks kind of like an E. It's actually a Greek letter S, capital S, and it stands for sum. So it looks like this. Okay, that's the Greek letter sigma. Okay, and we'll talk about that tomorrow. I do want to do one quick thing. Let's see. Okay, we've been using this for a while. Hopefully everybody's been here and has seen this. There are the notes. I'll upload the videos that I record in this chapter and everything. The homework is right here. Okay, please do maybe 10 or 15 problems on the homework. Just do some of the stuff like we talked about. Please don't get too far ahead. Don't try and finish the entire assignment. This is the assignment right here, and here's a calendar of what's coming up. It's going to take us about 2 weeks to cover most of Chapter 7, and then we're going to take some time and start doing some probabilities and statistics and getting ready to take the end-of-year exam. Okay? Any questions? Yeah. Nope. Hang on to them. All right. Have a great day.